My name is David Nguyen. Today I'm going to be talking about my work named Reducing Smartphone Application Delay through Read-Write Isolation. And I'm from the College of William & Mary. So our work addresses the real-world problem, which is the application delay, and it actually spans two things. One is the application launch. Second thing is the runtime delay. I'm going to talk about that later on. The research questions that we are trying to address are following. First, how does disk I/O affect smartphone application response time, and how to optimize storage to improve application performance. So we are trying to address the application performance from the storage perspective. Our contributions are threefold. First of all, we conduct first large-scale Android I/O study on the 2,600 devices, and we propose a new scheduler named Smart I/O that reduces application delay, and our evaluation indicates 21% reduced launch delay, 17% reduced runtime delay. In order to collect the data from 2,600 users, we utilize our application that we developed. It's called StoreBench, and it's also available on Google Play, so please feel free to try and test out the application. One of the main findings that we found was regarding the I/O wait. So let me explain briefly what is actually I/O wait and why it is actually important. I/O wait is a CPU active time spent waiting for storage I/O. So roughly, you can think of it as a part of a total time that your device actually spends waiting, idling for I/O within its lifetime. And our results show that 40% of devices spend between 30% to 58% of the lifetime waiting for storage I/Os, which is pretty significant. If we were able to somehow reduce this part of the idling, that would be great, and that would contribute to reducing application delay. You will see that we succeeded partially, and we hope that the community will help us to even improve that. So to conclude here, it's a significant CPU time spent waiting for storage I/O, and this actually motivates us to question what actually might be causing such waits, right? And it turns out that it's due to partially to a I/O slowdown that I'm going to talk about very briefly now. And the main thing is that reads actually are experience up to a 600% slowdown when blocked by concurrent writes. So it means that when you have reads going on and writes going on in the background, reads are slowed down significantly. All right. So we came to this notion based on our measurements. Here we had 10 simple runs of where we issued first. When you take a look at the blue color, that's the sequential read and a low. Next, the red color, that's a sequential read with concurrent write, and you see that there is a huge jump, right? Huge slowdown. Similarly, random read as well. Okay. So this I/O slowdown, we think that is a possible source of worse application launch. Why? Well, because when you launch an application, obviously there are a lot of reads going on mainly. So reads dominate. So this might be causing that, right? So reads are slowed down by writes significantly. The question is whether it is also the other way around, whether writes are slowed down by reads, because that might affect our solution. Thankfully, actually, it is not the case, and there is a huge asymmetry between read slowdown and write slowdown. When we take a look at this experiment, where we have sequential I/O and random I/O, and we have your slowdown ratio. When you take a look at slowdown ratio of read slowdown, so that's the black color, that's huge, right? While the write slowdown, that's much smaller. Similarly for random I/O. So just to be clear, read slowdown, that's the response time of a read in the presence of a concurrent write over response time of a read when running alone. And write slowdown, similarly, that's response time of a write in the presence of a concurrent read over response time of a write when running alone. So the main observation here is that read slowdown is up to 6.15, while write slowdown is just up to 1.6. So let me just summarize this small study. Android devices spend up to 58% of CPU active lifetime idling due to I/O. That's the first point. Second point, reads experience up to 600% slowdown when blocked by concurrent writes. And there is a large slowdown asymmetry. So the question is, how can we actually utilize that? Well, in our solution, we propose a new scheduler that is built on the state-of-the-art CFQ. And the basic idea is very simple, actually. We are just giving higher priority to reads and lower to writes. You can think of it as a simple application of the shortest job first, right? So we are actually doing the shortest job first because on Flash, actually reads are super fast while writes are super slow. Okay. So that's a simple reasoning. Our solution is based in the kernel space, and the I/O scheduler has three basic components. The I/O priority assignment that assigns just higher priority to reads and lower to writes. Those reads and writes are then following grouped, and then they are dispatched. There is also a so-called concurrency profiler, which we elaborate more in the paper, but roughly, you can think of it as this. When you issue a big workload with, say, 2 processes, it's fast, right? But if you divide that workload to, say, 4 processes, it's even faster. But when you increase this number of processes, keep increasing that number of processes, you will hit a certain threshold beyond which there will be such a huge overhead of managing, and you will not see an efficiency. So the concurrency profiler actually just tries to get the optimal number of I/Os that are to be issued at the same time. So how does it work actually in practice? Each flash block device has 17 queues of I/Os, right? And what happens is that they are divided into 3 groups based on the priorities: real time, best effort, and idle, where real time is the highest priority and idle the lowest priority. And these I/Os actually are selected and inserted into a so-called dispatch queue. All right. So in our work, we actually don't change this structure. What we do is that in addition to that, we reorganize the dispatch queue so that from the bottom up, they are organized as real time, and then best effort, and then idle. Well, but how are they organized? They are reorganized based on the class, okay? And also based on the priority within the classes from 0 to 7, where 0 is the top priority. Okay. And And we reorganize them so that from the bottom up we have real time and best effort, then idle. The big thing here, what we have is that reads precede writes. Okay. So you see, the design is very simple. Let me show you a quick demo. Okay, so you can see that first we use a Samsung device and we use a screen so that you can see what is actually going on. We are issuing a command that launches a YouTube application. All right. So first of all, we will launch the application without our solution. Okay, and we measure the time. You see that it's 0.86 seconds. Okay. So that's the real time without our solution. And now what we need to do is that we need to clean the caches. We need to clean the application data. And again, we relaunch the application, the YouTube application, and let's see what happens. So first of all, we need to enable our scheduler. You will see that it's in addition to Smart I/O, we also have a new deadline CFQ available from the state-of-the-art, and we use the time command to measure that time. And now it's 0.781 seconds, which translates roughly to 17% of saving. All right. So with gain comes obviously also cost, right? Let's take a look at the Nexus 4 device. What do we have there? So the first slope in the Nexus 4, that's sequential read, right? When we issue a one reader and one writer, 128 megabytes, what you see is that in the sequential read, okay, so that's the first slope of the first subfigure, okay, you see that the sequential read SR slowdown improves from like roughly 6.15 to 1.72. Well, how about the write? Write, sequential write, that's the next two slopes, SW, okay? You see that we actually have the write worsening a little bit from 1.13 to 1.51. So that's the cost. That's where the cost comes. How about the random read? Random read slowdown improves from 3.18 to 1.97. And the write worsens from 1.6 to 1.83. So that's, again, gain and cost. You can take a look at more discussions regarding other devices. All right, so next we also evaluate our solution and we compare with other schedulers. So other state-of-the-art schedulers are CFQ, Deadline, New, and ours is Smart I/O. And the solid case, that's sequential I/O, and dashed lines are random I/Os. And the very simple experiment we issue is 128 megabyte mixed workload. Mixed workload means in the first case, we have 10% of reads, 90% of writes, then we increase to 20% of reads, 80% of writes, so that we have the variety. And what we can see, right, is that with increasing percentage of reads, the response time decreases, which is reasonable from our discussion, because we have less writes. It also means less slowdown, right? And by changing the scheduler from the default CFQ that we have in the state-of-the-art, which is the blue color, you can see to the pink color, which is the Smart I/O, we can achieve up to on average 49% improvement. We also evaluate our solution on different situations, such as cold lunch delay, warm lunch delay, and runtime delay. Cold lunch delay is clear. You don't have data in the cache, while warm lunch delay, it's in the cache. Runtime delay, that's just a time that is required to complete a predefined set of user events issued by Android Monkey. And What we can see is that cold launch delays are reduced on average by 21%, okay, and warm launch delays only by 30%. So the question is why? Well, because when we have cold launch delays, a lot of IOs are going all the way to the storage, while in the warm launch delay, you have a lot of data already in the cache and in the memory, so not many IOs going on. So all the way to the storage. That's why we don't benefit much there. And runtime delays are reduced by 70%. We can also take a look at closer at say one application, say 25. You can see pretty interesting saving for cold launch delay. Warm launch delay, not much. Runtime delay, not much, right? So, in order to evaluate fully, also on the application layer, we have two ways to do that. Well, we can use a smartwatch, or we can use a stopwatch. That's imprecise, right? Or we can modify the code just by adding some timestamps. So that's what we did with a Facebook application, and we evaluated on 5 devices, cold launch and on warm launch. Just a perspective, Facebook Inc. actually its goal is to have cold launch delays less than 5 seconds on 2012 or newer devices, and less than 10 seconds on older devices. So how about our case? When you take a look at the Razer, for example, that's the last slope in the cold launch, you can see that's the reduction from 9.9 seconds to 6.2 seconds, while Samsung S5 from 3.7 seconds to 2.3 seconds, which is very interesting. For warm launch, we achieve less, which is expected. So let me just conclude here. I introduce this. We introduce a system named Smart I/O that reduces application delays through read-write isolation and higher read priorities. As far as our future plans, we plan to study our other stages of application lifecycle, install, update, switch, and so on. And also we plan to analyze impact of network I/O. And for Wing, I would like to extend thanks to many folks who contributed to this work, and also our shepherd, Professor Satya from CMU. And this, I will conclude my talk, and I'll be happy to take questions. Thank you.